All right, so jumping in late on the recording, take the derivative dy dt, and you get all the pieces, and they give you everything you need to fill in the blanks, and you can stop here for a safe stop. Calculator ready, meaning if it's ready to be typed in the calculator, then you don't need to do it. You can let the calculator do it, or you can just stop there. And so that answers the question of, before we've had things that were only algebra, but they weren't solved for what we were looking for. And you guys are like, hey, can that be safe stop? Because it's all algebra. Like, well, it is all algebra, but if it's not calculator ready, then it's not a safe stop. You gotta get what they're looking for by itself. Then you can safe stop and leave it alone. Questions on this one? It's as simple as we can make them. Usually they're going to be word problems. So let's read some kind of hints on, or steps on, solving a word problem, and then we'll do a few together. Draw a figure if possible. Come on, you've been in math forever, and that's always a word problem tool, is draw a picture to help see what's going on. Number 2, assign variables and restate the problem. I think that means restate the problem in terms of your variables. So put things in, translate it into math. They're going to give you an English problem. You're going to translate that into math. Listing your given information and what you're asked to find. Be careful with the positive or negative. We had that yesterday with it increases versus decreases. So it won't always say negative. It'll say decreases, and you got to just be paying attention to catch that. But all of that, number 2, I would say, is translate English into math. All right, students have long felt that math was like a foreign language. Just going to embrace that and say, yeah, it kind of is. So translate the paragraph into, condense it down into calculus stuff, algebra stuff, equation stuff, variables. Make it a math problem instead of an English problem. Number 3, find an equation that relates to variables. Find an equation that relates to variables. So look at the things they give you, and then think back, okay, well, what do I know about those things? If it's the 3 sides of a right triangle, well, that's Pythagorean theorem. If it's a radius and area, well, that's pi r squared. So look at what they give you. That will point you to the equation that you need. Once you have the equation, by the way, sometimes they'll give it to you if it's a weird problem that's not an equation we expect you to know, like surface area of a sphere or something kind of weird. They'll probably just give it to you. Differentiate that with respect to time. That's what we did yesterday. That was those previous examples on the last page, page 2, 1 through 16. So you've done 16 of those. So that's not really the hard part of the problem. And then substitute in all the stuff you know and solve for what you don't know. So that part's not hard either. Probably the hardest part is step number 2. Translating it from English to math. Once you turn it into a math problem, this is always the case with word problems, right? Once you get it into a math problem, it's fine. It's just getting it from the English to the math. All right, let's try number 1 together here. And for the first couple, I think it really walks you through step by step the process. I don't expect you to write out all this stuff every time. I don't expect you to write out any of that stuff every time. But it's nice to do the first couple where it really explains what we're doing. All right. A pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. Circles, that probably matters. The radius of the outer ripple is increasing. There's a lot of good words in here. At a constant rate, so that's derivative. When the radius is 4, find the rate at which the area of the disturbed water is changing. Draw a picture. Okay, let's draw a picture first. I think maybe a top-down view of the pond. That way we'll see the circle going out. So there's our concentric, or our circle. There's the radius. We've dropped in that's not like a fixed pond. That's the That's the concentric circle, the wave that's moving outward. Your diagram doesn't have to be that detailed, but stuff is changing, and so if you need to somehow draw that into your picture, so that these are all rate problems. Stuff is changing about them. Assign variables and restate the problem, meaning translate all that stuff into math. Right? The radius of the outer ripple is increasing at a constant rate of 1 feet per second. How do I translate that? What does that mean in math? What is equal to 1 foot per second? This was the page 1 stuff. How do I translate a sentence into a variable? Again, use the units. Is it r equals 1 feet per second? Yes or no? Some of you are like, a few of you are saying no. No, r would be a foot, not a foot per second. And it said it's a rate, so this is dr dt. The radius is changing at 1 foot per second. When r equals 4, it's got to have a little bit of English still. We can't translate it all. When r is 4, find the rate at which the area is changing. So what are we trying to find in terms of calculus variables? Rate of the area. So how do I phrase that with calculus variables? So it's not a, because that'd just be area. dA dt. So I'm looking for dA dt. Notice whether things are positive or negative. That was, the RDT is positive, it's getting bigger, that makes sense. Step 3, find an equation that relates the variables. Okay, relates to variables, but never including t. You don't have to worry about t, because when you take a derivative, that's where t is going to show up. So find an equation that relates the other variables. So r and a for a circle. How about area equals pi r squared? Differentiate with respect to time. Again, that's what you did yesterday. That was the homework from yesterday. So dA dt. In fact, I think we did this one 2 or 3 times within that homework yesterday. Equals 2 pi r dr dt. Step 5, substitute the given information. Solve for the unknown derivative. Be sure to include units with your answer. I know the units already, because if I'm trying to find dA dt, that's going to be feet squared per second. So I've got my units already. By the way, sometimes, even on the AP test, if it specifies to give units, usually the units are worth 1 point. On a free response question, all free response questions are worth 9 points. If it specifically asks for a unit, that means it's worth 1 point. Which means even if you don't know how to solve this problem, if you said, units are feet squared per second, you'd get a point. And the name of the game on the AP test is get all the points you can. So even if you didn't know what else was going on, hopefully you could figure out that dA dt would be feet squared per second. All right, so back to our problem here. We're looking for dA dt. That means we need to know the other stuff. R is 4, and the RDT is 1. So we've got everything we need. So 2 pi I'm going to put the units on there. I already know what the units are going to be. Oops, that goes backwards. Put it right here. R is 4 feet. And the RDT is 1 foot per second. So 2 pi times 4 would be 8 pi. Feet times feet is feet squared. And second is in the bottom. So that's how fast the area of the circle is changing. Again, the name of the unit is related rates. The rate of the radius changing is related to the rate of the area changing, according to that formula that we came up with. Number 2, ladder problem. Guaranteed there'll be a ladder problem on the test. Always is. There's usually one on the AP test, and you'll see why in a minute. A 13-foot ladder is leaning against a wall. A 13-foot ladder is leaning against the wall. Okay, be careful here. 13 feet. Where is that going to go in my picture? This messes some people up. Yeah, here you're like showing me the hypotenuse. The ladder is 13 feet long. So don't put 13 feet. It's not how high up the wall it goes or how far from the wall it is. The ladder is 13 feet long. Suppose that the base of the ladder slides away from the wall. So this would be a bad situation if you're standing on the ladder. But the base of the ladder is going to be sliding away at a constant rate of 3 feet per second. How fast is the top of the ladder sliding down the wall? Okay, this makes sense. If we slide the ladder down the wall, if the bottom is sliding out, the top is sliding down. And we want to see how those rates are related to each other. We're going to need some variables in here. I think A and B and C would be great choices, because that is a squared plus b squared equals c squared. And I need to label them something so that I can make sense of the rest of this problem. I can translate into math now. So the base of the ladder slides away from the wall at a constant rate of 3 feet per second. So what is equal to 3 feet per second in terms of my picture? Can you tell? Gonna get popsicle sticks out after. You guys are too quiet. What's changing at 3 feet per second? A, B, or C? A. So dA dt, it can't just be A because A is a length. Feet per second is a rate. So dA dt equals 3 feet per second. Is it positive or negative? Is A getting bigger or smaller? Bigger. A is getting bigger. So dA dt is getting bigger. dA dt is positive. How fast is the top of the ladder sliding down the wall? So what's it asking me to find in terms of my variables? dB dt. So I want to find dB dt. When the base of the ladder is 5 feet from the wall. Well, it doesn't spell it out, but that means A equals 5. All right, I think I've translated all it has to offer me into math. So I got a picture, I did my translating, now I need an equation that relates them all. A squared plus B squared equals C squared. find a relationship among the variables that lets you eliminate one variable. We'll talk about that in a minute. We don't need to do that just yet. Differentiate with respect to time. We did this one before. 2a dA dt plus 2b dB dt equals 2c dC dt. All right, we're trying to find dB dt, which means we better know everything else. So let's look and see if we know everybody else. So A is 5, we know that. dA dt, we know that. B, we don't know B. So we'll have to figure out what that is. dB dt is what we're looking for, so we don't know that either, but that's what we're looking for. C, we know, that's 13. dC dt, we don't know. So I've got a little extra work here to find B and dC dt before I can find dB dt. Anybody know what B is equal to? 12. That's a 5, 12, 13 triangle. So this one's a little bit sneaky. It didn't give me exactly everything I needed, but I know enough to know that B is 12. A squared plus B squared equals C squared. So I know B. dC dt does not tell me what dC dt is. Anybody know what dC dt is? What does dC dt represent? So don't tell me what number it is. Just tell me what it represents in terms of the problem. The change in the length of C. It doesn't change. I mean, I guess you could have one of those collapsible ladder deals, but that's not this problem. That ladder is 13 feet long. So if it's not changing, what's dC dt equal to? 0. Because that's not changing. The change in the length of the ladder is 0, which is great for our problem because that's going to wipe out that side of the problem. So now we know, everybody. I guess we could divide by 2 if you want to just wipe out all the 2's, make it a little bit easier. So plugging in all the pieces, 5 times 3. I divided by 2, so all my 2's are gone. Plus, man, I got information all over the place. These problems, they have tons of variables in them, plus all the variables have a rate with them, so you got to be real careful keeping up with who's who. So B was 12. dB dt is what we're looking for. And C is 13, but that doesn't really matter because dC dt is 0. So a little bit of algebra. dB dt is negative 15 over 12. Let's see. B would be in feet. Time would be in seconds. Negative. So you can usually make sense of if your answer should be negative or positive. There's no way to figure out if it's 15 over 12 or not. But we can make sense of positive or negative. John?
So if it's 2a, why don't we multiply 2 by 5?
So I cheated and divided everybody by 2.
Oh, okay.
Just so I wouldn't have to deal with the 2's.
Yeah.
But I mean, I could have put the 2's back in there and it would have been just fine.
Yeah.
Does it make sense that this one is negative? Look at our picture. And some of you are nodding your heads. Yeah, that makes sense. The B is decreasing. B is getting smaller as the ladder slides down the... Right? You don't have to don't draw more pictures because that makes it more confusing, but as the ladder slides down, B is getting smaller, so it makes sense that our answer should be negative. Usually you can know ahead of time if your answer is going to be positive or negative because, the circle's getting bigger or the distance is getting smaller. And so usually you can figure out if your sign makes sense. Nobody's objecting. Obviously that will reduce, but who cares because we don't need to reduce. Was that your question?
Yeah. If you did reduce, it wouldn't be counted wrong.
It wouldn't be counted wrong unless you reduce wrong.
Okay.
That's the beauty of the safe stop and the danger of going further. If you're like, well, that'll reduce, and then you reduce it wrong, then you're going to lose a point. And if you'd have just left it, you'd have been okay. So safe stops save your time, but they also save you points in case you make a dumb mistake. Next example. Water runs out of a conical tank at a constant rate. Well, there's not a whole lot of conical tanks, but I guess that makes sense for a math problem. At the constant rate of 2 cubic feet per minute. The radius at the top of the tank is 5 feet, and the height of the tank is 10 feet. How fast is the water level sinking when the water is 4 feet deep? Well, there's a whole lot of information there. So translate it from English into math. So let's draw a picture and start labeling stuff. I think maybe this isn't immediately clear since you've never worked one of these problems before. But the only way this is going to work for a math problem is if our tank looks like that. If you did it the other way, if you do it this way, the water in there is always in the shape of a cone. If you turn the cone upside, well, I don't know which way a cone is, right side up or upside down. If you turn the cone the other way, then the water that's in there isn't always a cone. And so that's a whole separate deal if you got a shape that's not even a cone. So we don't want our cone to look like that. We want our cone to be such that the water is always in the shape of a cone. So our equation will always work. All right, well, I guess let's go in order. Conical tank, check. Constant rate of 2 cubic feet, 2 feet cubed per minute. Well, what is 2 feet cubed per minute? dV dt. And you could get that from the statement, or you could just get it from the units. Feet cubed per minute is volume per time. But it also tells you water runs out. Oh, speaking of runs out, what have I not got right? Negative, because it's leaving the tank. So the volume is decreasing in the tank at 2 feet cubed per minute. The radius at the top of the tank is 5. And the height of the tank is 10. Okay, so not the height of the water or the radius of the water, but the actual tank is 5 feet radius, 10 feet tall. How fast is the water level sinking? So what am I trying to find? In terms of calculus variables. How fast is the water level sinking? D what, dt? I'm going to call it h, but L is fine. That's this height. So find dh dt when the water is 4 feet deep, so when h equals 4. Let's think ahead on this one. Do we think the HDT is going to be positive or negative? If water is draining out of the tank, the height is going down. So I think the HDT is going to be negative, but we'll work the problem and find out. Okay, so I've got stuff about V and H and R. And so a formula that relates all those. This is probably one we would give you because we don't use volume of cones very much. It's 1/3 pi r squared h. Pause right there. Don't run ahead here. If I take a derivative right now, what rule am I going to have to use? Product rule. That's going to kind of not mess things up. I mean, we know how to use the product rule. But it does mean we'll have a dr dt and a dh dt show up. And I'd really rather not mess with that because I don't know anything about dr dt. Like I don't know anything about r at all, really, other than the overall radius of the tank. So R is kind of a problem child here if I peek ahead, because I get dr dt somewhere in this problem, and I don't know anything about dr dt. It would be nice, back here in step 3, if necessary, find a relationship among the variables. Is there a relationship among the variables? How are h and r related to each other? Whether they're at the top or whether the tank is halfway empty. How are h and r related to each other?
H is double the radius.
H is double the radius. It's a good way to say it. Could also said r is half the height. Same thing. H is double the radius. That means I can get rid of r over here and then not have to use the product rule. So be careful which one you solve for, right? If I get rid of h, then I learn all of my r stuff, but I don't have any r stuff. So I want to get rid of r. So r equals h over 2. So in place of r, I'm going to put h over 2 before I take the derivative. That way I avoid the product rule and I avoid a dr dt that I don't know anything about. This is probably the hardest piece of related rates problem, is figuring out how are these variables related so that I could get rid of one of them and not have to deal with the product rule. So 2 squared is 4, times 3 is 12. So for this particular cone, the volume is 1/12 pi h cubed. That doesn't work for every cone, but our special cone here, where the height is twice the radius, we can use this equation. This is going to be much better to take a derivative of. So find dv dt. In fact, why don't you see if you can finish the problem out, because I think you'll have everything you need. So see if you can take it from there, and then we'll come back and look at it. Okay, take a derivative. Got lazy and just put the 3 over the 12 because why reduce? Plug in the pieces that I know. I know what dv dt is, -2. I know what h is, that's 4. I'm trying to solve for dh dt. Only algebra is left, but this is not a safe stop because I don't have dh dt by itself. So there's a little bit more work to do. And so let's be careful. Remember, you can do as much work as you want. You've got to get dh dt by itself. But as far as actually multiplying the stuff out, you can... I'm going to be exceptionally lazy here. Maybe lazy is not the right word for it. I'm going to call it smart about things. So I multiplied by 12, divided by 3, divided by pi, divided by 4 squared, and that's my answer. Sure, I could clean that up, but why bother? It did say to include units, so I could do units by looking at the problem, or I could do units by looking at dh dt. dh dt is a lot easier to look at. H is in feet. T's in minutes, so feet per minute. Questions on that one? Obviously, when you look this up in CalcChat or back of the book or whatever, it's going to have this simplified to whatever it simplifies to, but we don't have to do that. All right, we probably have time for one more. Oh, angle. Yep, let's do the angle one. A fish is reeled in at a rate of 2 feet per second from a bridge that is 16 feet above the water. At what rate is the angle between the line and the water changing when there are 20 feet of line out? Yeah, that's a good first reaction. What? Well, draw the picture and then try to make sense of what's going on. A bridge that is 16 feet above the water. So here's the dude with the fishing pole. And the line is out here in the water. A fish is reeled in. So I think this is looking like a right triangle problem to me. So I think I'm going to go with A, B, and C. That way it fits Pythagoras. So A, B, and C. Fish is reeled in at a rate of 2 feet per second. What is the rate, the angle between the line and the water? So that'd be down here. When there are 20 feet of line out. Okay, well, translating this one is kind of tricky. So something's 2 feet per second. And it says it's a rate, so I know it's a d something dt. Looking at my picture, what is changing at 2 feet per second? In terms of the variables that I've got on there. C. So if we're reeling the line in, that line is getting shorter. Whoops, I just gave away the second answer there. If we're reeling it in, C is getting shorter at 2 feet per second. What rate is the angle changing? So find d theta dt when something is 20. Well, 20 feet of line, I guess that's C. You know what? I went with A, B, and C because I thought it was Pythagoras, but with the theta in there, that's not going to be a Pythagorean theorem. And that throws people off on this because they're like, ooh, right triangle. Like, well, yes, that's true, and that equation is true and will hold, but that equation doesn't tell me anything about theta. So it's not wrong, it's just not helpful. I need an equation that has theta for sure, and then dc and dc dt, so something about c, which is the hypotenuse. So I need an equation with an angle and a hypotenuse. And I'm starting to think about SOHCAHTOA. What was that? Well, I need hypotenuse involved. So TOA doesn't have hypotenuse involved, so TOA is out. Now I've got options. I can use sine, which is opposite over hypotenuse, and I can use cosine, which is adjacent over hypotenuse. One of those is going to be, either one would work. One of those is a whole lot better choice than the other.
Sine.
Why sine? You're right.
You know B already?
Because you know B, that's a good answer. What else do you know about B that makes it a whole lot easier? Think about rates.
It doesn't change.
B isn't changing. A is changing. So sure, I could write cosine, and then I'd have A changing and hypotenuse changing. It's Geez, let's avoid that. Let's pick the one that isn't changing. So let's go with sine because the opposite is constant. So sine of the angle is the opposite over hypotenuse. And since b isn't changing, this is tricky on these problems. It says when c is 20, but c is changing, so I don't want to put 20 in there. If something's not changing, I can go ahead and substitute it in. Alright, so sine of theta equals, I'm thinking ahead, I got to do the derivative of both sides. Do you want to do a derivative with c in the bottom, or do you want to do a derivative with c to the negative 1? I think so. If you leave it in the bottom, you got to do quotient rule. If you make it c to the negative 1, then you have power rule, and that's usually easier. So derivative of sine is cosine, d theta dt, that's what we're looking for, negative 16 c to the negative 2 dc dt. So let's see what we got. We're looking for d theta dt, which means we better know all the others. C we know, dc dt we know, cosine. I don't know the cosine, but I do know that the cosine is equal to adjacent over hypotenuse. So hypotenuse is 20. You know what adjacent is when b is 16? Yeah, it's a 3, 4, 5 right triangle. On a lot of these problems, you start to notice that they sort of rig them. I mean, it's hard enough as it is, but they kind of rig them to throw you a bone once in a while. Like, that's 12, so it's a 3, 4, 5, 12, 16, 20 triangle. So now I know that the cosine is 12 over 20. And again, why bother reducing? We're in calculus. We don't have to concern ourselves with that stuff. Almost out of space. Going into the next line here. So d theta dt is 16 times 2 over 20 squared. And then I'm going to move this stuff over. So times 20 over 12. And leave it like that. Radians per second. That's a brutal one, the angle one. The angles are tough. The last thing I'd say on this is we got positive. D theta dt is positive. Does that make sense in our picture? As we reel in the line, theta is getting bigger. So I think that makes sense. By the way, angles will always be in radians, so you don't have to worry about that. Angles are always in radians. If you use your calculator, we didn't need a calculator for this one, but keep it in radians. All right, today's assignment's from the book, page 153, 1 through 7, 11 through 17, 21, 25, 27, 29. Odd goes with all of that stuff. Sorry. Alright. A lot of those are the very straightforward ones. Some of the later ones are a little bit more word problem-y. Again, we're done with new stuff, really. We're just going to, tomorrow we'll go over some of those. Monday we'll go over some more. We'll do a review. So I'd say this, if you understand everything so far, if you really understood it all, you'd be ready for the test right now, because we're not doing anything new. But that's probably not anybody. So we got a few more days to review, tutor, however you want to phrase it, to get caught up.